even whole molecules. Buckminster fullerene, Buckyballs, are gigantic spherical molecules of 60 carbon atoms and have been observed to produce double-slit interference under special conditions. We have to conclude that each individual photon, electron or buckyball travels through both slits as some sort of wave. That wave then interacts with itself to produce an interference pattern. Except that here the peaks of that pattern are regions where there's more chance that the particle will find itself. It looks like a wave of possible undefined positions that at some point, for some reason, resolves itself into a single certain position. We also saw this waviness in position when we talked about quantum tunneling. In fact, several quantum properties like momentum, energy and spin all display similar waviness in different situations. We call the mathematical description of this wave-like distribution of properties a wave function. Describing the behavior of the wave function is the heart of quantum mechanics. But what does the wave function represent? What are these waves of, or waves in? Let's start with what we do know about the double slit result. We know where the particle is at both ends. It starts its journey wherever we put the laser, or electron gun, or buckyball trebuchet, and it releases its energy at a well-defined spot on the screen. So the particle seems to be more particle-like at either end, but wave-like in between. That wave holds the information about all the possible final positions of the particle, but also about its possible positions at every stage in the journey. In fact, the wave must map out all possible paths that the particle could take. We have this family of could-be trajectories from start to finish. And for some reason, when the wave reaches the screen, it chooses a final location. And that implies choosing from these possible paths. So what causes this transition between a wave of many possibilities and a well-defined thing at a particular spot? Within that mysterious span between the creation and the detection, is the particle anything more than a space of possibility? Okay, we're adding more questions than we're answering. We still didn't figure out what the wave is made of. In fact, the answers aren't known, but the various interpretations of quantum mechanics do try. Let's talk about the view favoured by Werner Heisenberg and Niels Bohr, who pioneered quantum mechanics at the University of Copenhagen in the 1920s. The Copenhagen interpretation says that the wave function doesn't have a physical nature. Instead, it's comprised of pure possibility. It suggests that a particle traversing the double-slit experiment exists only as a wave of possible locations that ultimately encompasses all possible paths. It's only when the particle is detected that a location and the path it took to get there are decided. The Copenhagen interpretation calls this transition from a possibility space to a defined set of properties the collapse of the wave function. It tells us that prior to the collapse, it's meaningless to try to define a particle's properties. It's almost like the universe is allowing all possibilities to exist simultaneously, but holds off choosing which actually happened until the last instant. Weirder, those different possible paths, those different possible realities interact with each other. That interaction increases the chance that some paths become real and decreases the chance of others. There's an interaction between possible realities that is seen in the distribution of final positions, in the interference pattern. That pattern is real, even though the vast majority of paths involved in producing the interference never attain reality. In the Copenhagen interpretation, that final choice of the experiment, of the universe, is fundamentally random, within the constraints of the final wave function. The theory of quantum mechanics produces stunningly accurate predictions of reality, and it's completely consistent with the Copenhagen interpretation. But this is not the only interpretation that works. There are interpretations that give the wave function a physical reality. Remember, we know that light is a wave in the electromagnetic field,